Trains on the Moon. Behold, the Ruzic Lunar Schooner.
What the fuck is this piece of shit?
This magnificent machine was created by Melanovis, and this video is a collaboration with him, and I highly recommend you go check out his YouTube channel and give him a follow on ArtStation. Both are linked below. We call this the Ruzic Lunar Schooner, named after both Dr. David Ruzic and his father, Neil Ruzic. David Ruzic is the Plasma Institute Director and Professor of Nuclear Engineering at the University of Urbana-Champaign, whose YouTube channel, Illinois Energy Prof, you might have actually encountered. But this vehicle is equally named after his father, Neil Ruzic, who wrote the book The Case for Going to the Moon, which had a serious impact on saving the Apollo program. And actually, the first video I ever made that I considered to be actually good was about this book and the impact it had. It even went so far as to inspire me to write my own book, and it is currently the oldest video published on this channel. So, a nuclear engineering, science YouTubing, moon book writing, Apollo saving family. I could not think of a more fitting name for this nuclear powered moon train. Before I dive into details, I want to mention that we have a full resolution diagram with notes that I'll post for free on my Patreon page. You don't have to become a member to see it. Patreon is just a good way for hosting these sorts of things and won't compress the image. But first, why are we even talking about trains on the moon? And why is this train on a road rather than on rails? Well, the amount of transportation demand even early on in lunar development might surprise you. One of the most promising and nearest term ways of exploiting the giant ball of feedstock orbiting Earth that we call the moon is using it to source oxygen exports to low Earth orbit. Assuming we can profitably get liquid oxygen to low Earth orbit from the moon, the current version of Starship consumes about 3,400 metric tons of liquid oxygen just to become orbital, and then it needs to be refueled to go beyond low Earth orbit. Lunar regolith is about 43% oxygen by weight, so for every single Starship that wants to go beyond low Earth orbit, say to Mars or anywhere else, we would need to process about 7,900 tons of regolith. That means 7,900 tons of regolith need to be excavated and transported some distance per trip. If only 10 starships want to go beyond low Earth orbit in a year, that's 79,000 tons per year. What is the best vehicle to transport these thousands of tons? Probably something like a simple open-topped hopper wagon, which can drive on the lunar surface. But is one wagon enough? Well, probably yeah, at first. But consider the benefits of LOX exports to LEO for stations and satellites and everything else. A LOX-rich LEO would remove so many constraints that the annual transportation demand will quickly climb higher than just 80,000 tons a year. And this is just counting one part of the emerging lunar economy. So very quickly, we'd probably need more than just one wagon to match the ever-increasing demand to move stuff on the moon. But wagons are easy to make. It's just a metal box on wheels. However, power systems, that which moves the wagon, the prime mover, are much harder and much more expensive. So it makes sense to carry multiple wagons per power system, rather than making a power system for every single wagon. Voila, we've just reinvented the land train. But lunar terrain is rough, and loose regolith requires a lot of energy to drive on, so it makes sense at first to compact the regolith into something like a dirt road. You could use something like a roller rover to do this, but it's also likely to just happen naturally after our land trains drive over the same spot a few times, like how dirt roads were naturally made by passing wagons and foot traffic. And just like with the dirt roads of old, eventually, at some point, that stretch of trail will see enough traffic that it'll make sense to pave it. But paved roads originated for foot traffic from humans and their animals, which we don't have on the moon, while industrial practices use something like rails, wooden poles from mines as far back as the 16th century, then plateways in the 18th century, and eventually the modern edge rail we all know and love. So wouldn't it make more sense to lay down some steel rails for our wagon train, since this is an industrial application, not concerned with general public mass transportation? Well, the main reason trains run on steel rails is because of their low rolling resistance. Rolling resistance, the force needed to get a load moving, is largely determined by a material's modulus of elasticity, also known as Young's modulus, and steel wheels on steel rails have an incredibly low rolling resistance, which is why trains are able to achieve such high levels of transportation efficiency. But steel is quite expensive to create on the moon because we have to refine regolith and import carbon. I mean, we can make it, and I've argued on multiple occasions why we should, but what if we could achieve that same level of rolling resistance, or even better, with a material that is much more abundant and cheaper to make than steel? Well, a recent paper was published about 8 months ago which brought some new information to light that sort of changes everything. It turns out sintered regolith, if done right, is likely to have an even lower rolling resistance than steel. Rolling resistance is determined by a few variables, how smooth and dry a surface is, but the main property that determines rolling resistance is a material's modulus of elasticity, also known as Young's modulus. This metric has an outsized influence on a material's rolling resistance, and since we have no moisture on the moon, if a material can be polished smooth, then the modulus of elasticity is the main metric we need to look at to know if a material's rolling resistance will be low. There is not a direct formula to calculate rolling resistance using modulus of elasticity, since rolling resistance is generally measured much more directly by measuring how many newtons you need to exert to push a load from rest to rolling on any given surface. However, rolling resistance primarily arises from the deformation of the wheel on the surface it rolls on, and modulus of elasticity is a measure of how much a material will deform under stress, like that of a wheel. So the higher a material's elasticity modulus, the less it will deform and the lower its rolling resistance will be. Generally, only non-porous ceramics and glass have higher elasticity moduli than steel. But then why don't we make rails or roads out of ceramics or glass? It actually isn't because these materials are too brittle. There are ways to fix that. Concrete is brittle. The real reason is because roads aren't actually concerned with minimizing rolling resistance like rails are. We actually want friction on regular roads for traction control, which is why cars have rubber tires. So what would be the point of plating a road with ceramics? Rails are concerned with rolling resistance, but steel and concrete are cheap and abundant, and the manufacturing lines for everything rail and road are established and scaled, and much of the industry's knowledge and practices have been perfected over hundreds of years and grandfathered in. But on the moon, we have no cheap steel, and as we'll discuss, sintered regolith is more affordable. And we have no established industries. We have to rebuild everything from scratch anyway. So we might as well think outside the box and consider using non-traditional materials as the conditions are very different. Also, it's worth noting that we do actually make ceramic bearings and wheels here on Earth today because of its superior rolling resistance. So this is not completely without precedent. The real issue is, and the reason this hasn't really been discussed before, is that sintered regolith has generally always been much more of a porous type ceramic, with high porosity leading to brittleness and a much lower elastic modulus, orders of magnitude less, like around 8 gigapascals versus the 306 gigapascal sintered regolith created by the authors of this recent paper, published in June of 2024. This study measured the physical, mechanical, and thermal properties of vacuum-sintered lunar regolith simulant at different lower-end sintering temperature ranges. That part's important. And found that regolith sintered at precisely 1050 degrees Celsius has the best properties. Sintering is not melting, but it's close. When we melt something, all the individual particles turn into liquid and get mixed together, and when it cools, they reform as one solid mass. If we melt regolith, then pour that liquid into a mold to shape it, and then let it cool and resolidify, we have cast the regolith. And we generally just call this cast regolith. When we sinter something, the individual particles are heated enough to get soft and fuse together, but not fully melt and mix together. They are welded, not mixed. Sintering is what's done to turn clay into pottery, and it's how we generally make ceramics. Lunar regolith sinters between 800 to 1300 degrees Celsius. On the lower end of that spectrum, between 800 and 1000 degrees, the particles aren't fused as strongly together and the sinter is weaker. Above 1060 degrees, the individual particles will fully fuse or weld, but some melting will occur, which will release gas and create pores, which will make the sinter weaker. For example, this paper from 2017 measured sintered regolith's properties and found the regolith to have an elasticity modulus of only about 8 gigapascals and a much worse tensile and compressive strength as well. But the regolith sintered in the study was done at a much higher 1200 degrees Celsius temperature, which led to the sample having 1.4% porosity, and it wasn't sintered in a vacuum like the samples in the more recent study. We don't know the porosity percentage of our 1050 degree sample, but by just looking at the SEM pictures, we can tell it's very low. So it turns out the key to a really good sinter lies in getting as close to the line as possible. Let's call this the line of porosity, and approaching but not crossing it will give the highest fused particles with the lowest amount of pores. Since this line of porosity appears to be somewhere around 1060 degrees, it explains why the regolith sintered at precisely 1050 degrees had the best properties in the study, as it got very close to that edge, but didn't cross it. So this goes to show that going forward, it's not enough to just achieve a sintered brick in the lab made at some random temperature. We need to begin testing and forming our data based off the better sintered samples. Otherwise, we might be dismissive of things which would otherwise be great solutions. For example, if I had made this video just 7 months ago, before this newer paper was published, I wouldn't have known sintered regolith had such good properties and would have dismissed it as a bad building material based on the traditional properties, and the conclusions of this video would be totally different. Anyways, steel's modulus of elasticity is about 205 gigapascals. The regolith sintered at 1050 degrees modulus of elasticity was 306 gigapascals. Since the regolith has a 50% higher modulus of elasticity, will its resistance be 50% lower? Well, again, we don't have a direct formula to know what the regolith's rolling resistance will be, but I think it's safe to say it should be lower than that of steel. But by exactly how much, we don't know. So let's just say it has the same rolling resistance of steel, about 0.002. And if that's the case, what would be the point of ever using steel? We know sintered regolith will be cheaper than steel. Creating the vacuum and high heat required to sinter regolith is energy intensive and therefore expensive on Earth. But on the moon, we get the vacuum for free, and we can reach extreme temperatures very easily by concentrating sunlight, and we can sinter larger pieces of regolith using a radiative furnace heated by a solar concentrator mirror array, a solar radiative furnace. I plan to make an entire video on this specifically, so for that reason, and for time's sake, I won't go into solar furnaces too much now, but the main idea is that we can sinter regolith on the moon using sunlight. We get the regolith basically for free and the sunlight basically for free. There will be a cost per ton of sintered regolith, but it will be small, derived from the cost to make the solar radiative furnace itself, amortized across all batches made during its entire lifespan. Unfortunately, we don't know the cost to make this furnace, but considering its mostly simple parts, made in situ, the cost shouldn't be too extreme. I don't think it's unreasonable to assume something in the range of tens of megawatt hours, and if this is the case, and if it can process hundreds or likely thousands of tons of regolith, then the cost to sinter the regolith should be in the kilowatt hours or even watt hour range, basically a rounding error. Now, the best argument against all of this is that since sintered regolith is much more brittle than steel, it will break more often, and the maintenance costs for the roadway over time might amount to more than the extra upfront cost of just going with steel rails. And this would definitely be the case if we kept our vehicle's wheels as thin as that of train wheels on railways. But this is not a fair comparison. Imagine a modern freight train running on a concrete road. Of course its wheels would fracture and break through the concrete, But by widening the wheels, we distribute the load across a wider area, which actually leads to an even lower rolling resistance. And the 1050 degree sintered regolith has a tensile yield strength of about 12 megapascals, about twice that of modern concrete, which is between 2 to 5 megapascals. So this sintered regolith is stronger than concrete. Now this gets us into design a bit too, as it's not as simple as just laying sintered plates on the ground. In both cases we need ballasts for stability. On the moon we can use cast regolith, which should be incredibly cheap, cheaper than even the sintered regolith, as it could be melted in an open refractory, sunlight beamed directly into it, unlike with the sintered regolith, which needs to be in a radiative furnace. So we are talking about paving sintered regolith plates or slabs on top of a cast regolith subbase, similar to how we pave roads today. And this cast regolith subbase will serve to absorb shock impacts, as cast regolith has about 5 times the compressibility of concrete and even sintered regolith, and a higher tensile strength, so it will serve to dampen what impact shocks do occur. But if cast regolith has these better properties, why even bother with the sintered stuff? Why not use the cheaper cast regolith for everything? Well, remember, rolling resistance is influenced by modulus of elasticity, and cast regolith has a much worse modulus of elasticity than both the steel and sintered regolith. The ceramic-like sintered regolith has an amazing modulus of elasticity, but it has less compressive and tensile strength than that of the cast regolith, although it still has more of each than concrete, which is really saying something. But by combining these two materials together, the cast and sintered regolith, we reinforce their respective weaknesses with the other strengths, and we get a winning combination that is guaranteed to be cheaper than steel. However, a lot of the cost of steel comes from the fact that we need to import carbon to make it in bulk. About 60% of the cost of the steel rails comes from the import cost alone. So what about using just pure iron instead? Pure iron is weaker than steel in tensile strength, but its modulus of elasticity is about the same as steel, at 200 gigapascals, so we can assume a pure iron rail, while needing a different architecture, will have the same or a very close rolling resistance to that of steel. But these iron rails will need a different design than that of the steel rails, because iron has much less tensile strength, which matters because the wheels loading a rail's head creates a tensile force on the railhead. Steel's tensile yield strength is 585 megapascals. Iron's tensile yield strength is just 50 megapascals. So to compensate, a pure iron rail's head would need to be 11.7 times thicker. At this point, it wouldn't even be a rail, it'd just be an iron plate. And the sintered regolith surface is also essentially made of plates, or tiles, or pavers, or whatever you want to call them. So what we are talking about in both cases is a roadway. The only real difference being the exact material we choose to lay on top of the cast regolith base. And we already know that kilometer for kilometer, ton for ton, sintered regolith will be way less expensive simply because we can excavate regolith much more efficiently than iron, as iron is only about 12% of regolith's mass. Even more, non-mineralized free iron, the kind we'd be collecting with that cheapest of iron collecting methods, that magnet beneficiation technique proposed by William Augusto in 1981, makes up only 0.5% of the regolith's mass. So we'd need to process 200 tons of regolith for a single ton of iron. For a single ton of sintered or cast regolith, we'd only need to process something like 1.5 tons of regolith. Assuming all else is the same, to compete with the sintered regolith, collecting iron would need to be roughly 133 times cheaper than collecting and melting regolith. And even if you do somehow bring down the cost by this much, which would be about 64 watt-hours per kilogram processed, you would also be, at the same time, bringing down the cost of the sintered regolith, because all the regolith you collect to beneficiate iron from is regolith which can be sintered, so the goalpost will always move, and iron could never win. And add to all that the fact that we're assuming sintered regolith has the same rolling resistance as iron, when remember, in reality, it should actually be lower. So by this point, it should be quite obvious why a sintered regolith paved road would be much cheaper than a paved iron road. The main construction cost of a centered regolith road will be that of terrain manipulation, moving obstacles, creating level gradients, and compacting the ground upon which the road will lay, and that of transporting the cast and sintered regolith components across many kilometers to their final destination. We can simply call this process deployment. If we make our road 6 meters wide and half a meter thick, including the cast base and centered surface, given the cast and centered regolith have a density of about 2 grams per cubic centimeter, each kilometer of road will need to move 6 million kilograms of mass per kilometer, or 6,000 tons per kilometer. But we can move this mass on the part of the road already built. Assuming a rolling resistance of 0.002 equal to that of iron or steel, again, it should actually be less, we get a cost of just 3.24 joules a kilogram a kilometer, or 0.9 watt hours per ton, for a cost of 5.4 kilowatt hours per kilometer built. This is just the transport cost of the materials. It does not include the cost of sintering and casting regolith, or loading and unloading and installing, and it increases per kilometer built from the production location. But it should serve to give a sense of what we're talking about here. It's not that expensive. So how much would it cost to make one of these roads across the entire moon? A circumlunar roadway. Well, the moon's circumference is 10,921 kilometers. If we produce all of our road components from a single central hub, using our 5.4 kilowatt hours to transport materials for 1 kilometer of road per 1 kilometer of distance, then we can build in 2 different directions at the same time, 5,460.5 kilometers in either direction, and the cost increases linearly in both directions. So to find the total build cost of a circumlunar roadway, we can use this arithmetic progression formula, which will give us an average build cost per kilometer of 14.746 megawatt hours per kilometer, and a total build cost of 161 gigawatt hours for the entire lunar circumference. This is about as much energy as New York City consumes in a day, or 1 million people consume in 2 weeks, or about 2 weeks worth of output from a medium-sized power plant. Okay, I know we're just kind of wilding out right now, but look, if someone told me before I did this research that it would cost about as much power as New York City consumes in a single day to build a high-speed guided roadway around the entire moon, I wouldn't believe them. And this is a high-end estimate, as it only uses one central hub to produce the materials, which is kind of stupid. If instead we have 4 hubs along the route, all equally spaced out, then the total cost would be a quarter of what it was with just one hub, about 40 gigawatt hours. With 8 production sites, it would be 20 gigawatt hours, and with 16 sites, it'd be just 1 gigawatt hour. Now, I'll admit, framing it this way is kind of misleading, as I make it sound like setting up production sites is a free cheat code to lowering the cost, when in reality there will be an additional cost in setting up those production sites. But we'll want to use those hubs for much more than just building a single road. We can do a lot more with solar furnaces and centered regolith. These aren't Department of Transportation staging sites, these are the seeds of industrial hubs for everything we might want to do on the moon. Where you can center and cast regolith, you can build structures, landing and launch pads, habitats. This is just the beginning. One day each of these sites could have their own mass driver. Anyways, this kind of gets into developmental patterns. These essentially serve the same function as frontier towns. The US wasn't settled and developed from one single giant city, but Brazil was, which is one major reason why the US looks like this, while Brazil looks like this. This is what we call a primate city, which is one that vastly overshadows all other cities in its country in terms of population, economic activity, cultural influence, and political importance. Examples often cited include Paris in France, Rio de Janeiro in Brazil, and Seoul in South Korea. Primate cities have advantages and disadvantages, but one major disadvantage is they can often stifle development, which was one of the major reasons that motivated Brazil to relocate its capital, or maybe I should say build a new capital in the middle of the country, Brasilia, hoping it would encourage more development in the interior of the country. So there's advantage in having smaller distributed centers across the moon rather than just one central mega hub doing everything. Now, I get some comments about how strip mining the moon will mess up the tides and kill us all, and people who think that seriously underestimate the size of the moon. If you take an area 1 square kilometer in size and excavate just 1 meter deep, you'll yield about 1.6 million tons of regolith, enough material for 266 kilometers of roadway. From all that we know, regolith is between 5 to 10 meters deep at any given point. So taking the lower number of 5 meters deep to build a road around the entire moon, we'd need to excavate an area of only 8.2 square kilometers. For reference, Germany's Hambach mine is 44 square kilometers, or 5 times the area we'd need. So, to build a circumlunar highway for the amount of energy New York City consumes in 2 hours, we would really only need to build 8 sintering and melting solar furnaces, make 8 copies of all the needed vehicles, and excavate a single square kilometer 5 meters deep at 8 equal distant points across the moon. I don't know if 8 is optimal or 16 or 32 or whatever, but the point is the more we have, the more we can do, and it really isn't that much to strip mine the moon.
Oh my god, like, can we talk about like the
Actual train you showed at the beginning of this video? Oh, right. So this monster is powered by 4 Brayton cycle small modular nuclear reactors rated for 1.5 megawatts electric each. And the vehicle's total power output is about 5.7 megawatts, which should be enough to handle all mechanical and auxiliary power needs, and would be capable of hauling 75 cars measuring about 2 kilometers in length. Unfortunately, I'm not able to show this vehicle in its full 75 car 2 kilometer glory, as my hardware just couldn't handle that amount of rendering. But I should note that we haven't actually done any proper mechanical rolling analysis, nor can we reasonably provide any figures for vehicle mass or wheel torque speed. So this is just a high-level design with ballparked educated guesses. It's hard science fiction concept art. So these nuclear reactors turn hot rocks into electricity via the Brayton cycle, which uses helium as the working fluid in a closed loop to convert nuclear heat into mechanical work and then electricity. Because this cycle typically operates at very high temperatures, it can achieve high thermal efficiencies compared to traditional steam-based nuclear power cycles, and this allows the reactors to be more compact. Powerful machines and power electronics create lots of heat, and since there is no atmosphere on the moon, there is no convection to help us with thermal management. So our radiators tend to get very large. About 19 megawatts of waste thermal energy will be created by these nuclear reactors, which is why this radiator is so long. Sometimes size does matter. It's true that the length of this will affect how steep a road could be, its grade, but our lunar road should already deviate to mostly being straight and flat, with very shallow grades, similar to modern railways here on Earth. For the radiator, we need a fluid that has high thermal conductivity and low viscosity. Sodium potassium alloy, or NaC, is probably our best candidate. While we don't have many fluids on the moon, we have a good amount of sodium and potassium, which, when combined, create a eutectic mixture, which means the melting point is lowered more than that of the constituent elements. NaC is a liquid at room temperature, but also has a very high boiling point of 785 degrees, so it can remain a liquid across a wide range of temperatures. But more importantly, it is a metallic liquid, and as such it has very high thermal conductivity, which is why it's become an increasingly popular coolant in nuclear reactors and high-temperature gas turbines, and even some CPU coolers. High-performance radiators typically favor carbon composite materials, but on the moon we are constrained in access to carbon, so it's better to use something more abundant and investigate ways to increase its emissivity. This design was made with sheets of inconel alloy in mind as a conservative measure. However, simple iron should work as well, and would be significantly cheaper with higher emissivity. Emissivity is an especially important property for the radiator, and non-reflective dark surfaces have higher emissivity. One way to achieve this in metals that are normally somewhat shiny is to oxidize them. So we can actually apply an oxide layer to increase emissivity, however it might deteriorate over time and need to be reapplied. For this task, we have this cool radiator assembly maintenance robot, which can reoxidize the radiator sheets while also cleaning off any accumulations of fine static lunar dust. The Prime Mover module includes everything else needed to turn nuclear energy into power, such as 2 primary 3-phase transformers, an inverter module, rectifiers, switchgear and batteries with their own management systems, a hexapodal telepresence robot arm, and even a habitat for engineers, which entails a life support system with an emergency photovoltaic power supply attached on top of the transformer. This is also where the positioning and communication systems will be located. All of the components on the Prime Mover also generate heat, so the Prime Mover needs a secondary radiator to manage the thermal load. Instead of directing this heat into the main radiator, a separate system is necessary because the nuclear radiator operates at an extremely high temperature, around 677 degrees, but the components on the Prime Mover, besides the reactors, shouldn't generate more than 70 degrees of heat. So unless we use heat pumps, the second law of thermodynamics dictates that heat can only flow from a hotter object to a cooler one. However, 70 degrees is cooler than the lunar daytime temperature of 121 degrees. So this radiator employs an unfolding parasol sunshade, which can be positioned around using one of the Waldo modules, which possesses a telescoping boom. In this design, the parasol sunshade has 2 layers that meet in the middle, like a very flat hourglass. This is because infrared will be dissipated from the first sunshade layer as it heats up, which can be reflected out by the second. This is how the James Webb Space Telescope's multi-layer heat shield works, except this application is much more simple. As for why we shouldn't use heat pumps, well, it's true that the Planck blackbody power emission equation says hotter is more efficient since T is set to the 4th power. But heat pumps also add a lot of extra complexity and points of failure, as they're notorious for wearing down over time and have more moving parts than traditional pump accumulator approaches. So it's probably best just to have a secondary radiator instead. Needless to say, this train is going to be a major investment, so much so that we might want to have it continuously manned by engineers for the sake of responding to faults, which is why we've included a comfortable 3-person habitat. But it would be a real pain if the engineers had to enter and exit through the airlock anytime they wanted to do, well, anything outside of the habitat, including just inspecting the vehicle. If something goes wrong, engineers might have something like a 3-minute window for rapid inspection to figure out how to move ahead. Rapid EVA suit-ups are factored into this design, but assuming we're using hard shell suits, it can still take around 15 minutes. So it makes sense to employ a large robotic arm with cameras and tools to allow the engineers to observe the train and perform routine tasks from within the comfort of their living space. This is exactly why we have the Canada arm on the International Space Station. When fully extended, this thing looks crazy, like there's a giant stick insect riding on top of the train. We call it the lobster. But it will allow the engineers to perform physical checks and balances outside of what we get from SCADA, from any location, whether that's inside the cabin or even Earth. And it can even be used for dust cleaning operations, as each end effector has a little dust cleaning brush which can be pitched out. The top of the telepresence rig has a pair of star trackers for attitude determination. This is useful because there is no magnetic field on the moon, so we cannot use compasses. So the star trackers are there to help with pointing the rig. As for the train cars themselves, they are pretty straightforward lunar adaptations of modern train cars. However, they can be scaled larger and carry more mass than trains on Earth for the same amount of power and friction. This first car represents a tanker design for gas or liquids, while the rest are closed-top hoppers designed for bulk transportation of loose regolith. On the side of each car are rails with a mounting point for a cleaning Waldo. The wheels of these cars use an electromagnetic-based braking system in order to eliminate exacerbated erosion due to the vacuum environment, such as cold welding, as the brakes do not actually contact the wheel. The cool thing about electromagnetic brakes is they are basically just motors, which means with the appropriate power electronics, we can actually have regenerative braking for every car. So that's the nuclear-powered moon train, the Ruzic Lunar Scooter. Thanks for watching, and oh, I almost forgot. On the off chance you have issues importing nuclear reactors, we have also designed a solar-powered version of this train. As you can see, the main difference in this configuration is every car has its own solar array, and the Prime Mover does not have a massive radiator. Oh, and yes, of course these arrays can yaw 90 degrees to move out of the way for loading and unloading the cars. Having a solar array on each car means each car effectively provides its own energy, although each car doesn't have its own motor, but rather delivers electricity forward across a global DC bus to the prime mover. But each car is bringing its own electricity to the table, whereas with the nuclear-powered prime mover, each car is taking energy from a fixed amount provided per the mover. So a likely advantage of this solar-powered version should be the ability to haul more mass because each car is net power positive. The solar-powered prime mover also doesn't need a massive radiator, although now each train car does need a little one. So we still have a massive amount of radiator surface area, it's just distributed across the entire train rather than concentrated into one area. But this means for the same mass and volume as the nuclear version, you can have a larger electric motor on the prime mover to handle more energy input from more cars. So for the same size prime mover, you should be able to have longer trains and haul more mass. But this comes at the cost of added complexity per car. Think about this from a manufacturing perspective. You can either have a quite complicated nuclear-powered prime mover and a bunch of relatively simple cars, concentrated complexity, or you can have a relatively simple prime mover but with more complicated cars, distributed complexity. No single solar-powered car should be as complex as a single nuclear-powered prime mover, but adding them all together will result in more complexity per train. Or maybe you can measure it in complexity per million tons or something. And of course the solar-powered system can only work during the day, since the lunar night is too long for batteries to be reasonable. However, this aligns with the broader lunar economy, which will primarily function during daylight hours, as we discussed in the episode on solar cells. But this solar train should allow us to have less imports than the nuclear train, although it won't be zero imports, and there's an advantage in solar cells just being less politically reactive than importing nuclear reactors. I mean, we've sent nuclear reactors to space before, but they've all been quite small. It's still sort of iffy whether or not a company will be able to launch a larger nuclear payload to orbit or to the moon, or if the risk will just be perceived as too big to do so. I mean, I can totally imagine if Russia or China said they were going to launch a peaceful nuclear reactor of several megawatts in magnitude into orbit today. The US would probably be quite concerned it may not actually be that peaceful, and vice versa. It looks like a good way to plant nukes in orbit. And even if the entire global population was supportive of it, think about the paperwork involved. And what about insurance? So yeah, the solar cell approach has a quite significant advantage from this perspective as well. Even if it costs more, it's just simpler to navigate politically. But there are trade-offs. It really isn't a question of which is best. Both have advantages and disadvantages. So it really depends on the situation at hand, and we just wanted to offer both options for consideration. Now, I'm sure by this point, lots of you have already left a comment about using a third rail to power the train, but that would have the same problem as just laying aluminum transmission cables on the lunar surface: field emissions. Basically, an exposed electrode will have field emissions, which is when electrons basically jump off the conductor surface, and this will initiate micro or bulk discharges randomly along the whole rail, which would result in system failure. Here on Earth, this doesn't happen because the atmosphere acts as a pretty good insulator, and a lot of insulation on lower power cables is just there for safety reasons, not really to stop the system from failing. But on the moon, we are operating in a hard vacuum exposed to the solar wind, which will greatly enhance the field emissions. There might be a case to be made for induction, but that would require manufacturing magnets along the entire length of the roadway, which is a massive investment if the roadway is very long. So it probably doesn't make sense for longer distances. But induction might make sense in areas of high traffic, shorter distances, which is pretty much where we use third rails and cables on trains today. They're all mostly in urban areas. So maybe in some sort of manufacturing hub, induction will make sense, but that's a topic for another day. Thanks for watching. Please subscribe to Melanovis's channel and follow his art station. And as always, the biggest thanks goes out to the Patreon and channel members who make this work possible. Thank you.